Okay, so children, today we will discuss about energy. Okay, ICSC and class. So children, what is energy? Energy is defined as, please mute your audios, capacity to do work is called energy. Capacity to do work is called energy, and same like work, its units also joules or hours. Joules or hours. Okay, and there are different kinds of energies which we will study here, children. So mainly, of course, potential energy and gravitational kinetic energy, but there are different types of energies we are going to study. What are the some of different forms of energy? Just let me say. Then I will discuss in briefly about potential and kinetic energy. What are the different forms of energy we have, children? Solar energy we have, heat energy we have, light energy we have, light is also a chemical energy we have, hydro energy we have, electrical energy we have, nuclear energy we have, geothermal energy we have, wind energy we have, sound also is a form of energy, magnetic energy, magnetic fields, mechanical energy. Okay, so many forms of energies are there, children. All these energies, we will study. And children, energy is neither created nor destroyed. But remember always, energies can only one form of energy changes to other form. That is called as the law of conservation of energy. One form of energy changes to other form. No one can create energy nor destroy energy, but we can convert one form of energy to another form of energy. Okay, children. So normally, children, if you see, yeah, I will give a simple example, children. Dynamo. Dynamo means generator. In dynamo, what happens, children? Mechanical energy. You will move the wheel by using diesel or kerosene. It will start rotating. Electrical energy you will get. In dynamo, mechanical energy is converted to electrical energy. Suppose iron box is there, your iron box. If you switch on the current, electrical energy is converted into heat energy. If you see loudspeakers are there, in loudspeakers, children, electrical energy are converted into sound energy. It increases the sound. In battery, if you take, children, electrical energy is converted into chemical energy, or chemical energy is converted into electrical energy. Okay, and in candles, chemical energy of the candle is converted into heat energy and light energy. Like this, different energy conversions we will come across in our daily life. So many energy conversions you will see to the children. Okay, by making electromagnet, what happens, children? Current electrical energy is converted into magnetic energy. Nuclear energy, nucleus will break and liberate large amounts of energy. Okay, when water starts falling from dam, okay, that energy, potential energy is converted to kinetic energy. Like different forms of energies will come across in our daily life. Okay, so on the whole, at nutshell, today I want to discuss important energies called as potential energy and kinetic energy. I want to discuss. We'll discuss in briefly potential and kinetic energy. Only potential and kinetic energy we'll discuss. Slowly, listen, children. What is potential energy and what is kinetic energy? Any body which is at certain height will have potential energy, not on the ground. Any body which is moving will have kinetic energy. What is potential energy? Energy possessed by virtue of its height or position. Height or position is called potential energy. At the same time, energy possessed by virtue of its motion. If it is moving, means kinetic energy. That's all. If it is moving, means kinetic energy. Compulsory body should have certain position or height, and here compulsory body should move. Okay, children. And the formula for potential energy is mgh. Formula for kinetic energy is half mv square. Units are for both of them. It is joules only. Okay, we'll see how do we derive potential energy, how do we derive kinetic energy. Potential energy derivation is very easy, children. See, potential energy derivation will show you. Okay, so we know W is equal to F force into displacement. In the last class, I told you force is equal to force into displacement. All the work done in moving a body up is converted into potential energy. Potential energy is equal to, according to Newton's second law, what is force, children? M, A, and S. But when a body is moving upward, A we will write as G and S we will write as H. So potential energy formula is mgh. When a body is going in straight line, we'll write A. When a body is moving up or down, we'll write G. And S will write as H, mgh. Potential energy derivation is mgh. Compulsory body should have certain height, position, then only. Some examples of potential energy. Some examples, famous examples of potential energy. A stretched bow and arrow. A stretched bow and arrow. You stretch it and leave. All the potential when you are stretching, potential energy. When you are leaving, potential energy changes to kinetic energy. A tightly coiled spring, full potential energy will be there. When you release it, all the potential energy converts into kinetic energy. And water in a dam, because water in a dam is at great height. Because of that great height, all the water will have a potential energy. When you release water, they fall. Potential energy converts into kinetic energy. These are some of the famous examples of potential energy. Kinetic energy examples. Any moving body you take, children. Any moving body. Sometimes I will ask you, children, what is the energy possessed by aeroplane or bird? Can anyone say? What is the energy possessed by aeroplane or bird? Can anyone say? Yes, girls, anyone? What is the energy possessed by aeroplane or bird? Is it potential energy or kinetic energy? Anyone, girls?
So sorry, can you repeat?
What is the energy possessed by aeroplane or bird? What is the energy present? Potential energy or kinetic energy? Which energy is present in both of them?
I think potential.
Bird or aeroplane, they are flying at some height and they are also moving. So they will have both potential and kinetic energy.
Okay.
Airplane and bird, which is moving at great heights, will have both potential and kinetic energy. And kinetic energy derivation, I'm showing all of you. Please listen. Kinetic energy derivation. Kinetic energy derivation comes under work energy theorem. Kinetic energy comes under work energy theorem. All of you see here. W is equal to force into displacement. W is equal to force into displacement. W is equal to M into A into S. We know from third law of motion, v square minus u square is equal to 2as. Okay, so as we can write as v square minus u square by 2. Here I will substitute. So instead of as, I will write v square minus u square by 2. Okay, so work is equal to all the work, this 2 I'm bringing out, half m v square minus u square. This is work energy theorem. This is work energy theorem. Half m v square minus. If body is starting from rest, if body is starting from rest, initial velocity will be 0. If body is starting from rest, initial velocity will be 0. If you substitute 0 here, all the work done is converted to kinetic energy. Half m, anyway u is 0 natural v square. This is the formula for kinetic energy. Kinetic energy derivation comes from work energy theorem. What is work energy theorem? Half mv square minus u square. And if the body is starting from rest, initial velocity is 0, it is half mv square. Kinetic energy. Okay, so this is called kinetic energy, half mv square. Okay, so this is the difference between potential energy and kinetic energy. So apart from this, I want to say something about law of conservation of energy. Law of conservation of energy. So I hope everyone of you understood these things, children. Everyone of you understood these things. I will send a picture also. I'll let you save it and go through it. I'll send a picture also. And apart from this, we'll discuss law of conservation of energy also. So children, law of conservation of energy. So girls, coming to law of conservation of energy. What is law of conservation of energy, anyone? Energy can neither be created nor destroyed. Energy can neither be created nor destroyed, but only can be changed from one form to another. You can't create, you can't destroy energy. You can change only one form to another. That we have to discuss in two cases, children. Three cases. One is simple pendulum. One is upward thrown bodies. And one is downward thrown bodies. These three things, if you study, you will understand, children. So each one I will explain. Listen carefully, children. If you don't listen carefully, you won't understand later. Your wish. Now, in the case of simple pendulum, I will explain first. Very easy one, that is. This is simple pendulum. This is mean position when it is not moving. If you take it to some height like this and release, it will go like this and again come back to like this continuously. It will be going like this, like, and this is mean position. This is called extreme position. Extreme position. This is also extreme position. At the mean position, children, it don't have any height. This is only maximum height for it. It don't have any height. So potential energy is zero. But kinetic energy is maximum. And at topmost position, from this position, this is mean position. Here it is having some height. Here it will have potential energy maximum, but kinetic energy is zero. Why means it will come like this, stops. It will stop. No, that's what kinetic energy. And again goes down and goes here, stops. Again comes down, goes here, stops. Again comes down. So when in this journey here, maximum speed it will have. That's why kinetic energy is maximum at mean position. Then you will ask, what happens in the middle, sir? In the middle, both potential and kinetic energy will have. But overall, you take anywhere. Suppose here 10 joules is there. Everywhere it will have 10 joules only. Everywhere it will have 10 joules only. Okay, here also 10 only. Here also 10 also. Here also 10 only. Everywhere it will have 10 joules. But energies may change. Here only potential energy is 10 joules. Here only kinetic energy is 10 joules. Here potential plus kinetic energy is 10 joules in the middle. That is what I am saying. One form of energy is converting to other form. One form of energy is converting into other form. But on the whole, energy remains same. That is called law of conservation of energy in the case of simple pendulum. Here, I could give you only one example, but in the next one, I will show you derivation, children. If you see, you will understand. Derivation, I will show you, children. Derivation. Listen carefully, children. Imagine a body you are throwing from the top. You are dropping. I will show you here how it have same energy. This is position A, this is position B, this is position C. In three cases, I will show you same formula. I will derive and I will show you. Let the body is at maximum height h. Imagine. Initially body is here. So potential energy will be mgh. You know formula. Kinetic energy, anyone? How much? Here kinetic energy and how much? Kinetic energy, how much, children, here? Anyone? Girls, kinetic energy, how much here? Here. Kinetic energy. Before dropping, kinetic energy is how much? Zero, children. So total energy here is potential plus kinetic energy. So potential is mgh, kinetic energy is zero. So the energy, total energy at the position A is mgh plus zero is mgh. Here there is no kinetic energy, only potential energy is there. Now at the position C, children, it will come and it will fall down here. Here, what is potential energy? Anyone? What is potential energy here? Anyone? At least at position C, what is potential energy? Anyone? Girls? I don't know what for reason also. Potential energy is zero, children, and kinetic energy is half mv square. Half mv square. Try to understand, but we know from equations of motion, v square minus u square is equal to 2as. Body is falling freely. Freely means u is zero. Body is falling freely. Freely means u is zero. Dropping is u is zero. And v square is equal to, because it is coming and falling, I will write as 2gh. So half m into 2gh, 2 to cancel, mgh. So here total energy is equal to potential energy plus kinetic energy. So potential energy is zero and kinetic energy is mgh. So total energy at C is also mgh. At A also it is mgh, at C also it is mgh. At A also it is mgh, at C also it is mgh. Now A is over, C is over. A also I prove mgh, C also I will prove B also it is mgh. Listen carefully, children. If you don't listen, you won't understand also. I don't know how much you are understanding also. So imagine this is at height x. Imagine from the ground this is at height x. Imagine this is from the ground at height x. B. Potential energy is equal to, always you have to take from the ground only. So from the ground mg h minus x, because from h, oh no, mg not h. Yeah, because total height is h. From the ground it is x. So potential energy is just mgx. Potential energy is mgx because we have to take from the ground only height. And kinetic energy, girls, all of kinetic energy is, girls, try to understand, half mv square. Half mv square. From second law of motion, v square minus u square is equal to 2as. Because it is falling freely, v square minus 0 square is equal to 2gh. But girls, you see here, how much distance it came, how much distance from height h you remove x. So v square is equal to 2g h minus x. 2g h minus x. Substitute here, half m v square is 2g, v square is 2g h minus x. 2 to gone, so mg h minus x here, mg h minus x. So slowly you see here, total mechanical energy at position B is potential energy plus kinetic energy. How much is the potential energy we have? mgh minus mgx plus mgx. This gone. Again we got mgh only. Even at position B also we got mgh only. Those who didn't understand, again I'm saying potential energy from the ground we should take, so mgx. Kinetic energy we should take from the top, half mv square. V square is how much? H minus x I kept here. I got kinetic energy as mgh minus mgx. I got kinetic energy as mgh minus mgx. I substituted here. Kinetic energy as mgh minus mgx. Potential energy is mgx. This gone. So here also mgh I got. Here also mgh I got. Here also mgh I got. Whatever may be the energy, the total energy remains constant. This is called law of conservation of momentum in the case of freely falling bodies. I'll send a picture. You check that. This is in the case of freely falling bodies. Yes, this is in the case of freely falling bodies. Now, let us discuss in upward thrown bodies, children. Upward thrown bodies. Children, I don't know how much you are understanding, but if you don't understand, you have to be careful. You have to go through and you have to practice again. Upward thrown bodies means a body is thrown up. It will go height like this. A body is thrown up. So when a body is thrown up, here potential energy will be zero because no height, but kinetic energy is maximum. Here potential energy is maximum, but kinetic energy will be zero. And in the middle, you will have both potential energy and kinetic energy. Let us take position A, B, C. But now it is going up. When it is going up here, so potential energy is zero, kinetic energy is half mu square. Let us say it is thrown with a velocity of u. Let us say it is thrown with a velocity of u. So kinetic energy is half mu square. Total energy is potential energy plus kinetic energy. Potential energy is zero. Kinetic energy is half mu square. So answer is half mu square at position C. This is at position C. Now children, let's go to position A, then we'll come to position B. Let's go to position A. Let's go to position A children. See here. At position A, kinetic energy is anyway zero only, no problem. But potential energy, let me say this is at maximum height h. This is at maximum height h. Potential energy is equal to mgh is the formula. mgh is the formula. And the maximum height formula is u square by 2g. From Newton's from laws of motion, maximum height formula is u square by 2g. G gone, mu square by 2. Mu square by 2 is half mu square. Now, total energy is how much at A? Potential energy plus kinetic energy. Potential energy is half mu square and kinetic energy is 0. So, answer is half mu square. Even at A it is half mu square. Even at C it is half mu square. Now, let us see about the B. Okay, from the ground, let us imagine it has went up to x. So potential energy is mgx. I told you always you have to take from ground. Kinetic energy is half mv square. What is the velocity at this point? What is the velocity? What is the formula for velocity, children? V square minus u square is equal to 2a. Yes, normally v square minus u square is equal to minus 2gx, because minus y, because it is going against gravity, and x is the distance it went. Okay, children. So v square, what I can write, this u square will come how? U square minus 2gx. Okay, children. So substitute here. When you substitute here, I am showing, when you substitute here, or please see here, children. When you substitute this here, so mgx plus half m u square minus 2gx. Okay, so mgx is like that only I'm writing, plus this into this is half m u square. This into this is half m into 2gx, 2 to gone. So mgx plus half mu square minus mgx, plus mgx minus mgx gone, half mu square. Children, even at position B you got same formula. At position C also you got same formula. At position A also you got same formula. Means total energy remains same. Because total energy means potential energy plus kinetic energy. Total energy remains same everywhere. Only one form changes to other form. That's all. Only one form changes to other form. Okay, but total energy remains same. So this is about the kinetic energy, the total mechanical energy in the case of upward thrown balls.